All right, so get this. Scientists are trying to build a detector that could pick up like the faintest whisper of dark matter, possibly even revealing secrets from the very beginning of the universe. We're diving into some seriously cutting-edge physics today.
It's true. This isn't some far-off sci-fi concept. This is a real research paper proposing a way to find these elusive particles that have been puzzling physicists for decades.
Okay, so back up for a second. I think everyone's heard of dark matter, but it's always felt kind of vague to me. What is it exactly, and why are we so obsessed with finding it?
Imagine you walk into a room and see a chair seemingly move on its own. You can't see what's causing it, but the chair moves, so something must be there. Dark matter is kind of like that.
Okay.
We can't see it directly, but we can see its effects.
Yeah.
Galaxies are spinning faster than they should based on the matter we can see, so there's got to be this invisible stuff holding them together.
It's like the universe's biggest game of hide and seek.
Exactly.
Yeah.
And this paper thinks it might have found a way to finally shine a light on one type of dark matter particle in particular.
Okay.
They're focusing on particles with a mass around something called the Planck scale.
Okay. Planck scale. That sounds familiar, but remind me what that is again.
So imagine you're trying to measure the width of a hair using a ruler meant to measure the distance between cities. The scales are just completely mismatched. That's kind of what we're dealing with when we talk about the Planck scale.
Okay.
It's the absolute smallest possible unit of measurement where our current laws of physics start to break down.
So we're talking unbelievably tiny, like smaller than an atom tiny.
Way smaller. It is mind-bogglingly small, and this is where it gets really wild. These Planck mass particles might actually be a direct result of quantum gravity,
Okay.
which is the theory that tries to unify gravity with the strange world of quantum mechanics.
So these particles are potentially the missing link between the biggest and smallest forces in the universe.
Yeah,
This is already feeling like a major clue in our dark matter mystery.
it is, but here's the catch, because
Yeah.
these particles originate from quantum gravity. They interact incredibly weakly with everything else. They're like ghosts, barely leaving a trace of their presence,
Yeah.
which makes detecting them a huge challenge.
Okay, so how do you even begin to study something that's essentially invisible, smaller than we can comprehend, and barely interacts with anything?
This is where it feels like we're entering the realm of science fiction. If these particles are practically ghosts, how can we even hope to find them?
That's the ingenious part.
Okay.
These scientists are turning to the strange world of quantum mechanics for a potential solution. It involves something called quantum interference.
All right, break it down for me.
Okay.
What is quantum interference, and how do you use it to find something that's practically inviolable?
Imagine you drop a pebble into a still pond. You see those ripples spreading out. Those ripples are like a particle's wave function.
Okay.
Now imagine dropping two pebbles close together.
Okay.
The ripples from each pebble interfere with each other, creating a new, more complex pattern. Even the tiniest change in one ripple will change the entire interference pattern.
That's quantum interference in a nutshell.
Okay, I'm picturing the ripples, but how does this help us find dark matter?
These researchers propose using a detector particle placed in a superposition, meaning it exists in two locations at the same time. Think of it like that double pebble drop.
Okay.
But instead of two ripples, you have the potential for interference from two locations of the same particle.
Hold on. I thought things couldn't be in two places at once. Isn't that like breaking some fundamental law of the universe?
That's the beauty of quantum mechanics. It plays by a different set of rules. And here's the kicker. If one of those dark matter particles passes by, even though its gravity is incredibly weak, it will still tug on both of those superposed locations ever so slightly.
So it's like the dark matter particle creates a tiny disturbance in the force field, or in this case, the interference pattern.
Exactly. And that, my friend, is what the researchers are proposing to measure. It's like listening for a whisper in a hurricane, but instead of sound waves, we're talking about detecting the most subtle warping of space-time itself.
Okay, I'm officially mind blown, but how do you actually build something that can pick up these gravitational whispers? Do we need to invent some kind of super-powered microphone?
It's not a microphone, but it's just as ingenious.
Okay.
They want to use something called Josephson junctions.
Josephson junctions. That definitely sounds like we're heading even deeper into the realm of advanced physics here.
It does sound complicated, but the concept is actually quite elegant. Imagine a sandwich with two slices of superconductive material as the bread and a thin layer of insulator as the filling. That's essentially a Josephson junction.
Okay, I can picture the quantum sandwich, but Why is this specific setup so crucial for the experiment?
The magic happens because of the way electrons behave in a superconductor.
Okay.
They can actually exist in a collective quantum state. And here's the best part. That state can be put into a superposition.
So that's how we get our double pebble drop effect on a microscopic level.
Exactly.
We have our superposed detector particle ready to be subtly influenced by dark matter. But how does this actually translate to measuring that subtle gravitational tug? Okay, we've got our quantum sandwich prepped and our electrons doing their best double pebble drop impression.
Right.
But how do we go from these microscopic ripples in space-time to an actual signal that says, hey, dark matter just passed by?
Imagine a whole line of these Josephson junctions like a microscopic fence. Now picture a dark matter particle zipping past this fence. As it goes by, its gravity, weak as it may be, can actually subtly change the energy levels inside each of those junctions.
So it's like each junction in the fence acts as a tiny sensor getting tickled by the dark matter's gravity.
Exactly. And that tiny tickle translates into a measurable change in the electrical current flowing through the junctions.
Okay.
It's like each junction is letting out a tiny beep, signaling that something just passed by.
But we're talking about forces and particles at the very edge of what we can even detect. This signal must be unbelievably faint, right?
Oh, it would be incredibly faint.
Like trying to hear a pin drop in the middle of a hurricane?
You're exactly right.
Yeah.
That's where the true brilliance of this idea comes in. Remember how we talked about electrons in a superconductor existing in a collective state? That collective behavior actually amplifies the signal, making it potentially measurable.
So it's like having a billion tiny ears all perked up listening for that same faint pin drop.
Yes.
That's amazing.
Precisely. And to give those ears the best chance of picking up the signal they'd need to be chilled to almost absolute zero, minimizing any thermal vibrations that could drown it out. Imagine trying to hear that pin drop in a silent room versus a room full of noisy toddlers. You need things to be as calm and quiet as possible.
Okay, so super chilled, super sensitive quantum ears.
Right.
What about all the other stuff out there? Wouldn't even the tiniest vibrations from the environment mess up the experiment?
Yeah.
It seems like trying to maintain that level of precision would be nearly impossible.
It's definitely a huge challenge, but the researchers have thought about that too. They've proposed some really clever solutions, like carefully designing the shape and arrangement of the junctions to filter out noise from certain directions.
Okay.
Think of it like noise-canceling headphones, but for gravity.
So after all this, are we on the verge of a dark matter breakthrough? Should I get the champagne ready?
Hold the champagne for now. That this research is incredibly exciting, but it's still very theoretical.
Okay.
Actually, building a detector like this would be pushing the very limits of what's technologically possible.
Right.
This isn't something we'll see next week or even next year. It's more like a glimpse into the future of physics.
But if it worked, that's a big if. But still, what would it mean for our understanding of the universe?
If it worked, it would be revolutionary. We'd be opening a window into a realm of physics we've only ever dreamed of, the realm of quantum gravity, the very first moments of the universe.
So we're talking about potentially rewriting physics, textbooks, maybe even our understanding of the Big Bang itself.
Yeah.
That's mind-blowing.
Exactly. And here's another exciting thought.
Okay.
This paper assumes that these Planck mass particles make up all of dark matter. But what if they're only a small part of the puzzle? What if there are other, even stranger forms of dark matter out there interacting with the universe in ways we can't even imagine?
You're saying we might be on the verge of not one, but multiple paradigm-shifting discoveries.
That's the beauty of science. Every answer leads to more questions, deeper mysteries. And in this case, those questions could unlock some of the universe's biggest secrets.
It's certainly enough to keep us all on the edge of our seats, waiting for the next big discovery. Thanks for diving into this mind-bending research with me today. It's been an incredible journey, and for you listening, keep that sense of wonder alive and stay curious, because who knows what secrets the universe will reveal next.